Okay, let's get started. So, hello everybody. Thank you for joining us today. So, welcome to the Astro 30 ECR Astronomer in Australia seminar series. So, my name is Marianne Girard. I'm a postdoc at Swinburne University, as my co-chair is Amelia Fraser-McKelvey, and she's a postdoc at University of Western Australia. So before we begin, it's important for us to acknowledge the traditional custodian of the land on which we meet today. So the Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing system of knowledge on which we continue to build. We acknowledge the traditional custodian of the unceded lands on which we are meeting today. So I'm speaking with you today from the land of the Yuhudjeri people of the Kulin Nation. My co-chair Amelia and our two speakers are joining us from the land of the Yadruk people of the Noongar Nation. We pay our respects to their elder past and present and extend that respect to all First people joining us here today. So today we have two talks. Each talk will be 20 minutes and we'll have 5 minutes of question at the end of each talk. So please save your question until the end of the talks. Feel free to use the chat function and you can write a question there and Amelia can read the question after to the presenter during the question session. So the talk will be recorded and they will be placed afterward on the Astro 3D YouTube channel. So by being here today, you also are going to the Astro 3D's meeting code of conduct. So the next speaker is Christene Lynch from Curtin University. So Christene, you can share your screen and I'll let you to your talk.
Thanks. Yes, hi, I'm Dr. Christene Lynch. I use she, her pronouns, and I'm a postdoctoral fellow at Curtin University, as Marianne said. And I'm a member of the Murchison Widefield Array Epoch of Reionisation project. And today I'll be presenting results from first half of a survey that I've been working on to improve the foreground models that this group uses to calibrate and do source removal for this project. And this work has been done with many members of the Murchison Widefield Array collaboration, but some key members who have really significantly contributed to the completion of this survey thus far are listed here. Okay, so moving on. So what's the big picture here? Why are we interested in the Epoch of Reionisation and trying to detect signals from this time period? What's shown here is kind of the basic picture of how we think the universe has evolved, starting off with the Big Bang, expanding and cooling and producing the cosmic microwave background. And then the universe entered what is called the dark ages. And during this time, the hydrogen and dark matter coalesced via gravity into the first luminous sources in the universe. So the first stars and galaxies. And it's these first stars and galaxies that then re-ionized the universe. And this marked the beginning of the Epoch of Reionisation, or the EOR, as I'll probably call it through the rest of the talk. And this is really the last transitional phase of the universe before modern day astrophysical sources. And while we have this overall picture of how the universe evolved, there are still a large number of unanswered questions about this cosmological model. And in particular for the Epoch of Reionisation, we want to know when exactly did these first stars and galaxies form, and what did these first luminous sources look like? What did the first galaxies look like, and how similar were they to the galaxies that we observe today? We'd also like to understand how these first luminous objects affected their surroundings and affected the formation and evolution of modern galaxies. And to answer these big questions, we're using observations of the 21 centimeter spectral line of neutral hydrogen. And hydrogen, as you might know, is the most abundant element in the universe. And because it's essentially everywhere, it's a really good choice to trace the evolution of large-scale structure in the universe. But also, kind of more importantly, the 21 centimeter emission is a spectral line. So it provides kind of this unique cosmological probe. So as the expansion of the universe will stretch the wavelength of this 21 centimeter radiation emitted from points in the past. And so by observing over a large range of wavelengths, we can map slices of the history of neutral hydrogen content in the universe. And this is kind of the ultimate promise of kind of 21 centimeter cosmology, is to do kind of a three-dimensional tomography of cosmic history. And these three dimensions are the two dimensions that are the spatial dimensions and a dimension in time based on the frequency of the observed neutral hydrogen line. And so what I'm showing here is an example of what we might expect for kind of a mapping of this neutral hydrogen across time. And these are from simulations. And so these are simulations showing the hydrogen content at different redshifts, with the bright regions indicating the location of ionized hydrogen and the dark regions indicating the location of neutral hydrogen. And we can, as we look towards lower redshifts approaching modern day, we notice that all of the hydrogen becomes ionized. And so we would like to actually observe directly this evolution of neutral hydrogen using radio interferometers. But today's radio interferometers are not sensitive enough to actually make images similar to these simulated images. The EOR signal is just buried beneath a bunch of, instrumental noise, many orders of magnitude of instrumental noise. But, not all hope is lost. Instead of making images of the neutral hydrogen, we can instead make a statistical measurement of the 21 centimeter signal. And the statistic that we are using is the power spectrum. And I'm showing here on the right an example of a one-dimensional power spectrum. So the power spectrum is essentially showing, as a function of three-dimensional spatial scale in a box of the universe, where the fluctuations in the neutral hydrogen are. And just to give a kind of a sense of where things are lying in this, right? So the vertical axis is the amount of power in these fluctuations. And then on the horizontal axis is kind of the Fourier modes associated with the different spatial scales, where larger spatial scales are associated with low K modes, and smaller spatial scales are associated with the higher Fourier K modes. And if we observe the power spectrum over many different wavelengths, they, as indicated in this figure as redshifts, we can see how the structure of the neutral hydrogen actually evolves statistically. And we can see how power moves between the different spatial scales as a function of redshift. And this will tell us how the galaxies are actually sourcing these fluctuations in the universe. Now, even though we have a way to actually detect this 21 centimeter emission from the Epoch of Reionisation, it's still a very difficult problem. It's a very big challenge. And the main challenges to the detection is that the signal is buried beneath basically all these other radio sources. So as Tristan showed, our telescopes aren't just sensitive to 21 centimeter emission from the EOR, but 21 centimeter emission from everywhere, radio emission from our Milky Way galaxy, as well as a sea of other radio sources in the nearby universe. And so these are the sources that are obscuring this cosmological signal that we want to detect. They are the foregrounds to the EOR emission. And these astrophysical foregrounds are roughly 4 to 5 orders of magnitude brighter than the 21 centimeter signal. So we really need a way to actually separate this signal that we want to study from all these other radio sources. And this has kind of been the main focus of the EOR community for like the last decade, trying to really separate these two signals. And so the EOR community has developed this formalism to try to distinguish between the EOR signal and the foreground signal using what's called a two-dimensional power spectrum. And if you've seen an EOR talk before, you've probably seen a lot of two-dimensional power spectra. And I'm showing here a simple example of one of these two-dimensional power spectra, where color is kind of indicating the power, and it's given as a function of two different Fourier modes. On the horizontal axis is the Fourier K perpendicular modes. And so these are indicative of spatial scale on the sky. So again, large K perp modes are corresponding to small angular scales on the sky. And these are kind of the angular scales on the sky that longer baselines of radio interferometers are sensitive to. And then at smaller K perp, you have larger angular scales on the sky. And then along the y-axis is the K parallel modes, and these are corresponding to the distances along our line of sight. And really the key to distinguishing between the EOR signal and the intrinsic foreground signal is that the spectral structure of these two components are very different. So the EOR signal is very spectrally structured. It has a lot of structure. And so it will have emission up at high K parallel modes. However, the intrinsic foreground is expected to have very smooth spectra, be spectrally smooth. And so we'll only occupy these low K parallel modes. And so you can see in this two-dimensional space, there's regions where you can look for the EOR signal without being obscured by these intrinsic foregrounds. However, once you get an interferometer involved, it gets a little bit more complicated. So our radio interferometer is inherently chromatic. It has its own spectral signature. And because of that, it actually moves this intrinsic foreground emission up into these high K parallel modes where we wanted to make the detection of the EOR. And so it basically is just spreading foreground emission up where we wanted to actually make our measurement. And to make things even worse, that is, if there are any errors in your analysis, say with your calibration, this adds to this spread up into these high K parallel modes. And so really the name of the game is kind of minimizing this spread, kind of trying to maximize this, what we call the EOR window, where we want to make our measurement by minimizing the errors in our analysis. And this really requires kind of two things, a really complete and accurate model of all of the astrophysical foregrounds, and a very deep understanding of our instrumental response and systematics. So that's kind of why it's very challenging to make this detection. So as I said, I'm part of the Murchison Widefield Array project. And if you don't know what that is, what the Murchison Widefield Array is, it's a low frequency telescope. It's sensitive to frequencies between 80 and 300 megahertz. It's made up of these tiles. So I'm showing this picture is pictures of the tiles in the compact configuration. And each of these tiles has 16 of these spider-like dipoles on them. And so the array has 256 tiles, 128 of which we can correlate. We're hoping in the future to be able to correlate all 256. And recently the array went through an upgrade. So now we have two different configurations of the MWA. There's a compact configuration that has a bunch of redundant baselines that's basically just used for EOR science. And then the extended array. So the extended array added tiles out to baselines that were twice as long as the longest baseline of the phase 1 MWA. And so with the extended array, we get much better angular resolution for our imaging. And we also end up getting a better point spread function as well. And so we're able to do much more sensitive imaging. And as indicated by the name of the array, the wide field array, it has a large field of view. So in a single pointing, the main lobe at 150 megahertz occupies 610 degrees squared. And really, with the full primary beam, you're sensitive to the whole sky. And so that has definitely pluses and minuses, as you'll see, particularly for EOR science. So for the MWA EOR project, we observed 3 different fields. The main 2 are EOR1 and EOR0. And these are located in the coldest parts of the sky and as far away from the galactic plane as we possibly can get. But because of the MWA's huge field of view, we're not able to actually avoid all of the bright extended sources in the sky. And you can see in EOR1, there are kind of 2 real bright points, and those are A-team sources, Fornex-A and PIC-A in that field. And so, yeah, so the MWA field of view really is not letting us be able to avoid those sources. And Pober et al. In 2016 actually looked at the effect of the wide field of the MWA on the EOR experiment with this telescope, and really looked at what the impact of these sources that are far from the center of your observing field are on the power spectra. And so what they did was to simulate, so what I'm showing here on the left is the footprint of the primary beam of the MWA centered on EOR 0 at RA of 0 hours and minus 27 degrees declination. And they simulated point sources in this primary beam and moved them far, incrementally from the center of the primary beam out to the side lobes and looked at what the 2D power spectra looked like. And that's what these are shown here. And you can see is that for a source located at the center of the primary beam has a two-dimensional power spectrum that's very different than one that's located out towards the side lobes, with the side lobe source having much more power extending up into these higher K parallel modes. And this kind of is expected because the chromatic effects of the interferometer actually become stronger far from the pointing center. And so you expect that these side lobe sources will contaminate these high K parallel modes. And so this paper really showed that these foregrounds are kind of a wide field contaminant. You can't just worry about the ones that are at the center of your field, in your main observing field. You do have to worry about basically the whole sky when you're observing the EOR fields. Additionally, the phase 1 MWA had an angular resolution of between 1 and 2 arc minutes. And so most of the sources in the sky were unresolved. And Procopio et al. In 2017 did a study to see how the impact of having a sky model that's based on images where most things were unresolved or point sources versus using higher angular resolution data to do more, to do modeling of particularly the extended sources, how that actually impacted the EOR science. And what's shown here in this figure is actually a comparison of an extended source that's in the galactic and extragalactic all-sky MWA survey, the GLEAM survey. And that's given by the contours. So the GLEAM image is basically the contours. And also this source is in the Giant Meter Wave Radio Telescope all-sky survey, the TGSS survey. And that's given by the image. And you can see that TGSS, which has a higher angular resolution, is actually giving you a lot more features to this source than the phase 1 MWA did. And so Procopio et al. Really wanted to understand what happens if you base models on the MWA data versus something like the GMRT. And they found that if you use a sky model that's based on just point source models versus a sky model that's actually using higher angular resolution data to model these sources more accurately, that you have a lot more residual power after calibration and source peeling when you're using these point source models. And they found a factor of 2 improvement in the residual power in the EOR window when they used the high angular resolution data from the GMRT to create the source models for the calibration and source peeling. And what they really found was that by mismodeling these bright extended sources, these are really the ones that are contributing the most power, excess power, when you're mismodeling them.
You have 5 minutes left, Christene.
Okay. So what's needed is to basically carry out this same analysis that Procopio et al. Did, but to do it for not just one field that they studied, but all the fields for the main EOR fields, as well as their neighboring fields. And that's kind of what we're doing with this Lobes survey, the survey that I'm conducting. So the long baseline Epoch of Reionisation survey is using the extended array of the MWA with the higher angular resolution and better imaging capabilities to observe the 2 main EOR fields and the neighboring fields. And we want to have multi-frequency information, so we cover 130 megahertz with this survey. And today I'll just be talking about the EOR 0 fields, so fields 1 through 5. So to create this sky catalog, I kind of followed the same process as GLEAM, where I made a deep wideband image that covered 60 megahertz, a mosaic 60 megahertz of bandwidth to do the source finding and source fitting. I then forced fit each of those Gaussians that were for the source models in each of the spectral images to make my spectral measurements. And then you can do spectral modeling using that information. And this is just an image of the declination minus 27 strip of this half the survey with a 5x5 degree inset. And you really can see the image quality from this, and that there aren't a lot of PSF features that were seen from the phase 1 data from the MWA. It's much cleaner with the extended array. And this is just some of the survey properties for the first half. So the first half of the survey covers roughly 3,000 square degrees and has almost 81,000 sources. It's 70% complete at 10.5 millijanskys, which is the 5 sigma limit. And the average RMS of this part of the sky for the survey is 2 millijanskys per beam, basically. And this is about a factor of 5 better in sensitivity than gleam. And this is also the most complete low frequency survey of these fields to date. And I'm showing the differential source counts here on the right in the brown circles as compared to some other low frequency surveys with similar sensitivities. And you can see that the Lobes survey agrees very well with those other surveys and is pushing down to some of the deepest sensitivities from the GMRT. Now, to really understand what improvements that Lobes is making for the EOR science, I looked at comparing the current sky model to what Lobes is putting out for a set of MWA data from phase 1, where I calibrated and peeled 1,000 sources from that data. And I'm showing a comparison of those peel residuals for the 2 different models. So this is the phase 1 data that I used to test the image of this source, overlaid with the current sky model, which is a single Gaussian. And this is the Lobes data overlaid with the Lobes model. And then these are the comparison peel residuals for those 2 models. And you see Lobes is doing much better. And if we look at basically the RMS, compare the RMS for these 1,000 sources as a function of angular size, you see that the difference in the RMS, where I'm taking the current model minus the Lobes model, the Lobes model is doing really well for most of these sources, and in particular, these large sources. And this is really due to the higher angular resolution. Now, to really directly compare the 2 catalogs, I used a simulation of MWA phase 1 data. And I'm showing that, and I did the same where I calibrated and peeled 1,000 sources using the 2 different catalogs, the current sky model used and the Lobes catalog. And I'm showing the 2-dimensional power spectra here for those 2, where this is the current and this is Lobes, and this is the ratio and the difference. And really the key takeaway is that there's a factor of 3 improvement in the residual power, foreground power on all angular scales when we use the new Lobes source models. And so this is really showing the kind of the impact of having this higher angular resolution imaging and better imaging quality on the ability to remove these foreground sources. Yeah, so I'll just leave my summary here, but I just really want to highlight that the Lobes survey is really pushing kind of the sensitivity limits of the MWA, and it is a very complete survey for these EOR fields, which is very important. And it's clear that in both data and simulation, the Lobes sky model is an improvement upon the current sky model used by the Australian MWA EOR group. So thank you for your attention, and I'll take any questions.
Fantastic. Thank you for such a clear talk, Christene. I think I finally understand power spectra now. So if we've got questions for Christene, you can raise your hand or pop it in the chat. Hamza, go ahead and ask your question.
Christene, thank you so much for a really nice talk. I had one question, actually connecting up with probably one of the previous MW papers. So this method, it improves upon the current limits, right? So do you have a sense of how much you expect the upper limits to come down?
Yeah, so it's not, so in the data, we're still limited, particularly in the EOR window at larger scales by some other systematics. So kind of the real impact of the Lobes models that we see in data is that it's definitely removing a lot of power from these smaller angular scales, which makes sense because of the better angular resolution. But just with Lobes alone, it's not real clear how much things will improve. But what really needs to happen is that we would take Lobes and then add to it a model of the large scale structure on the sky. So the Milky Way is a huge foreground for us. And we don't consider it at all currently in our sky models. And so I'm working with a couple other postdocs here at Curtin to try to actually make a model of the Milky Way to add to the Lobes catalog. And then we're hoping that by adding that component of the foreground, we are able to push down to further limits. I don't have an exact number that we think, but we do think that it'll make, you know, at least factor of 3, maybe an order of magnitude better limit.
I see.
We'll
That's the plan. Thank you so much.
Thank you. Other questions for Christene? Maybe while everyone's digesting what you said, I can ask a very simple question, which I'm sure has a very simple answer. The MWA's field of view is massive. Is there a way that you can design your telescope so that the field of view is smaller and so you don't have all of these pesky foreground sources in your way?
You could. So that the other low frequency telescopes definitely do have smaller fields of view. The MWA is really optimized for surveys. And I mean, the scale, the angular size scales that the MWA is sensitive to are very tuned to EOR science, but it does have that kind of, you know, double-edged sword where you have to worry about the whole sky. But there are lower frequency telescopes, and the SKA low will have a smaller field of view, but still you will have to worry about these sources. You can't just be focused just on that main lobe. They will end up, especially if they're towards kind of the edges of the main lobe or in the side lobe where things are very chromatic, there'll be a problem.
Sure, that makes a lot of sense. Any final questions for Christene? Well, if not, I will hand back to Marianne. Thank you.
Yes, well, thanks a lot, Christene, for your talk.